Yo, what's going on, physics class? It's your teacher, Mr. Lopez, and welcome to another lesson of Physics, Chapter 14. Today we're talking about the gas laws. Alright, let's go ahead and jump right into it. Okay, first off, just like springs and strings and pulleys, gases also have ideal forms. The ideal gas particles have no volume, so let's go ahead and highlight a few things just to kind of make sure that we're all paying attention to the important things. They have no volume. Ideal gas particles do not interact except when they have perfectly elastic collisions. So if you guys remember, elastic collisions were collisions that bounce off of each other, had no deformation, there's no energy loss in any way, shape, or form. Again, this is unrealistic for real life because most collisions are at least partially elastic. But perfectly elastic collisions and no volume, this is perfect for idea of ideal gases. Okay, so good starting point. Now, for this lesson, we're going to talk about the gas laws. And there are several gas laws that we should kind of be paying attention to. The first one we're going to talk about is Charles' law. Now, Charles' law deals with the effect of temperature on the volume of a gas, so temperature and volume on a gas at constant pressure. So if given a problem that's asking you guys, that's comparing a change in temperature or a change in volume, but there's no change in pressure, we want to go ahead and use Charles' law. All right, Charles' law was developed in the late 1700s by Jacques Charles. And also another physicist, which we'll talk about later, and they studied the effect of temperature on the volumes of gas at constant pressure. All right, they related the computation to the values of absolute zero as a temperature. So because they're using absolute zero as a guideline, that means that temperature must, and I cannot stress this enough, it must be represented in kelvins. All right, it will not work if you leave it in Celsius. And there are some textbooks and some tests out there that are going to try to trick you. I'm not trying to trick you. I'm trying to warn you of these tricks, where they're going to give you problems in Celsius, and we need to convert them to Kelvin. All right. This is what Charles' law is. It's a pretty simple and pretty basic and pretty, you can't even see that. It's a pretty simple and pretty basic proportion that says the volume, the first volume divided by the first temperature is equal to the second volume divided by the second temperature. All right, so this is Charles' law, but really huge asterisk for us. We just got to make sure that we understand that the temperature must be in Kelvin. Okay, so let's go ahead and look at a math problem, something that might be asked of you, and let's see if we can solve a problem using Charles' law. Example 14-7 in your textbook says, what volume will a gas occupy at 277 degrees Celsius if it occupies 0.5 liters at a volume at 27 degrees Celsius? Assume constant pressure. All right, so for this problem, what we want to do is we want to make sure that we have all this information, we understand what's happening in this problem. We have an ideal gas sitting that occupies this much volume at this temperature, and what's going to happen to the volume, because we're trying to figure out, well, what volume would we have if we raise the temperature to 277 degrees Celsius. So let's look at the information that we have. We have a V1, we're starting at 0, let's change the color of this thing. We're starting at, let's do this one, 0.5 liters, and it's going to, and at 0.5 liters, it is 27 degrees Celsius. Now, it doesn't matter which one starts and which one's finished because we're using proportion, and as long as they're together, as long as these two are on the same side, we're good. Now, one thing that I want to point out is in the very last slide, I pointed out to you guys that the temperature must be Kelvin, and already they're trying to fool you guys. They're trying to make sure that you don't get got, and we want to turn this 27 degrees Celsius to Kelvin. Okay, so what we're going to do is we're going to add 273 degrees Celsius, and that's going to give us our Kelvin value. We add these together. 7 plus 3 is 0. We have 300 Kelvin. Now, we're going to go ahead and look at the next volume. We don't know what the next volume is, so we're going to put an X. And the temperature that starts off is 277 degrees Celsius. Again, Celsius, we need to convert that to Kelvin. So we're just going to add 273 degrees. When we add these together, we're going to carry 550 Kelvin. We're going to put all of this information into our proportion. So 0.5 liters, 300 Kelvin. Next volume we don't know, so we're going to put an X and 550. And the rest can be solved using butterfly method. 0.5 times 550 divided by 300. I plug all of this into a calculator and I get 0.917 liters. Now notice my liters is the same unit that I started with, and besides temperature needing to be Kelvin, the volume could be in any type of volume, pressure. Those can be in any type of units. We just have to make sure they're consistent throughout the problem. All right, let's go ahead and look at Boyle's law. Boyle's law deals with the effects of pressure on the volume of a gas, and it's at constant temperatures. So if you are ever given a problem that deals with pressure and volume, but the temperature is constant, or maybe they don't give you any information on temperature, use Boyle's law. Invented what we call a Boyle's law tube to investigate this, and if we want to go ahead and look further at this, the volume is inversely proportional, blah 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 blah. This is the main thing that you want to make sure that you have for this one. Alright, this is the main equation that we're going to use whenever we have Boyle's law problems, where V1 times P1 is equal to V2 times P2. For this reason, let's go ahead and look at another example, and let's see what an example for 14-8 in your book has to say. Alright, it says a chemist collects 2.5 liters of oxygen. Alright, that's the volume. 2.5 liters of oxygen from a chemical gas generator at a pressure of 800 torr. 800 torr. Alright, and that's just a new unit of pressure. It could be in atmosphere, it could be in pascals, it can be in torr. The units don't really matter. As long as our answer is in torr and liters, we should be good. We're trying to find what volume, so we don't know what volume will the oxygen occupy at a pressure of 760 torr. So we're going from a 2.5 liter at 800 torrs of pressure, and we're decreasing the pressure, so we're trying to figure out, well, what volume should it occupy? So there's nothing that we have to really convert because we're not dealing with temperature. Everything can kind of get plugged in. So we have 2.5 times 800 is equal to X times 760. If I want to get X by itself, I divide on both sides. And I should be able to find my new volume. So our new volume is 2.63 liters, right? Because our original unit was in liters. So all of these are pretty straightforward. Our third law that we should talk about is Gay-Lussac's law. And this deals with the effects of pressure and temperature at a constant volume. So notice they give if we have a problem dealing with pressure and temperature, we're going to go ahead and use this. Again, the volume is constant, so there's no volume to be found in this problem. And this, I mean, we don't have to do a math problem like this because it works with the same exact way. But remember, if we're using temperature, then the temperature must be in Kelvin. Here's a comparison of all three laws and what you might have to find. Like in Charles' law, you would use it to find volume or temperature. But pressure is constant, meaning therefore they didn't give you any value for pressure that you have to use. For Boyle's law, you would find volume or pressure, but there's no temperature to use. And Gay-Lussac's law, you would find pressure or temperature, but there's no volume for you to find. All right. The combined gas law does not require that any single quantity remain constant. So if all of them can potentially change, if you have all three values, you can go ahead and use this ratio. But it also works vice versa. Technically, I guess you can use this for all of them because, like, let's say we have a problem that has a constant temperature. If they're constant, they cancel out on both sides, and then you end up with one of our previous gas laws. And this is true for all gas laws. All right. So if you want, you can use this one by itself and just kind of cross cancel. If they don't give you information, you can still use this. But maybe there's no constant values. Maybe temperature, pressure, and volume are all changing. Then this would be your go-to guy. The last real law that we should talk about is the ideal gas law. The ideal gas law is usually written as PV equals nRT. So here we have our ideal gas law. PV is equal to nRT. Where pressure and volume, temperature we're kind of used to, but we have two new guys to introduce to our lives. First, n, this should be a lowercase n. I don't know why it capitalized, probably just autocorrect. This should be lowercase n. Is the amount of particles, and that's usually in moles. All right, that's the unit that we're going to talk about. And the units for R must be consistent with the given data. So on the next slide, after you copy this down, we're going to go ahead and look at values for R based off a table in your book on table 14-4. Table 14-4 in your book gives you guys some examples where if you have value of n in moles, but the temperature is in Kelvin and the pressure is in Newton per meter squared and the volume is in meters cubed, you would use this value for R. But if you have the pressure as pascals instead of torr or newtons per meter squared, you would use a new value. Or if the volume is in liters, you would use one of these two values. But if the pressure was in torr, you would have to use this one. So this is a table based on the units they give you. This tells you what value of R you should use. There is something called STP, or standard temperature and pressure. And if there's ever a problem that gives you STP, that refers to these values for temperature and pressure. Standard temperature and pressure. For this problem, this is the temperature and this is the pressure. There will be problems that say at STP, and you'd have to use these values. And going back here at STP, all right, they would convert to Kelvin, and the pressure was in pascals, so that would mean you'd use this value for moles. Real gases, the ideal gas model is not accurate at higher pressure and lower temperature, so it has its limitations. And other more accurate and more complicated equations have been developed, like by Johannes van der Waals. Just kind of know that name, but for the most part, we're going to be sticking to all of our ideal gases. Again, real gases, not as accurate at higher pressures and lower temperatures, so for the purposes of our class, we're going to keep most of our stuff at ideal gas laws. So make sure you know the differences between all of these laws. All right. I think that's it. Have a good day. Have a good night. Whatever time it is. I don't know. See ya.